Do you know how scientists calculate the precise trajectories of distant spacecraft? It turns out that classical trigonometry on a standard flat surface is completely inadequate for this. Astronomers use special spherical triangles formed by the intersection of three great circles on a sphere. Their unique geometric properties allow for the flawless recalculation of coordinates for any observed celestial bodies.
If you want to chart the heavens or predict the dance of the planets, the simple, flat geometry we all learned in school just isn't going to cut it. The universe isn't flat. The paths of stars, the paths of ships on our own world, they're curved. So to really understand them, we need a different kind of geometry, the geometry of a sphere's surface. So let's dive into this absolutely essential mathematical framework, spherical trigonometry. So here's the game plan for this explainer. We're going to build this whole thing from the ground up. We'll start by defining what a spherical triangle even is, and then we'll see how its properties completely bend the rules of flat space geometry. From there, we're going to derive the absolute cornerstone of this field, that's the law of cosines, and see what other powerful tools it unlocks. And finally, we'll put it all to work in the Astronomers Toolkit. Okay, Section 1. Let's get right into it with an introduction to spherical triangles. We have to start with the fundamental building block of this entire field. So, what exactly makes a spherical triangle so special? Well, its sides aren't straight lines. They're actually arcs of what we call great circles. Now, a great circle is any circle you can draw on a sphere whose center is the same as the sphere's center. The easiest way to picture it is to think of the Earth's equator or any line of longitude. These are the absolute shortest paths between 2 points on a curved surface. Section 2. Let's talk about the properties of these triangles. Now that we know what they are, let's explore how they behave. And as you're about to see, they operate in a completely different geometric world, with rules that pretty much defy our everyday intuition. The first and honestly most startling difference is in the angles. In a flat triangle, the angles always sum up to exactly 180 degrees. No exceptions. But on a sphere, because the surface itself is curved outward, the interior angles are literally forced to be larger. Their sum is always greater than 180 degrees, and that's a direct consequence of the sphere's positive curvature. This extra amount, all the degrees beyond 180, is so important that it actually has its own name, the spherical excess. Think of it as a precise measurement of how much the triangle is deviating from being flat. A bigger spherical excess means you have a more prominent, more bulging triangle on the surface of the sphere. And here's where it gets really, truly elegant. That spherical excess, it's not just some abstract number. It is directly tied to the triangle's actual physical area. This formula here shows that the area is simply the square of the sphere's radius multiplied by that spherical excess, as long as you measure it in radians. It's a beautiful link between a purely geometric property and a physical one. All right, now for the main event. We are going to undertake a rigorous geometric derivation of the single most fundamental formula in all of spherical trigonometry, the law of cosines for sides. This right here is the cornerstone that supports the entire structure. To derive this law, we have to perform a really clever geometric construction. So imagine this. We start with our spherical triangle, ABC, sitting on a sphere with its center at point O. Then, from one vertex, let's say A, we draw tangent lines that just skim the surface. When these tangents meet the lines extending out from the sphere's center, we form two planar triangles. And that right there is the key. We've just created flat shapes that we can analyze with the familiar Euclidean geometry we already know. Now, the brilliance of this whole setup is that these two flat triangles, delta ODE and delta ADE, they share a common side, DE. So by applying the standard law of cosines that we all know and love to each of these flat triangles, we can write two different equations for the length of that shared side. See that? The left side of both of these equations is identical. It's DE squared. This is our bridge. This allows us to just set the right sides equal to each other, which in turn links the properties of the two planar triangles and, through them, the properties of our original spherical triangle. Okay, the next step is a bit of translation. We have to translate the lengths from our flat construction back into the language of this sphere. And we can do that. Using some basic trigonometry on the right-angled triangles within our figure, we can express every single one of those segments in terms of the sphere's radius in the angular sides of our original spherical triangle. Now, after you substitute all of these relationships into our equation and you just turn the algebraic crank, you arrive at the formal statement of the theorem. What it says in essence is that it gives us a direct relationship between the cosine of any one side of the triangle and the cosines and sines of the other two sides, and, crucially, the angle between them. And this is the result. This is it. The law of cosines for sides in a spherical triangle. This is an incredibly powerful formula that directly relates the lengths of the three sides to one of its interior angles. This is the primary tool for solving these triangles. So, with the law of cosines now established, with that under our belt, we can actually derive the other essential formula that are going to complete our mathematical toolkit for spherical trigonometry. From the law of cosines, we can derive other really powerful relationships. This one is often called the five-element formula. Now, its utility comes from the fact that it connects three sides and two angles all in one single equation. And that can be incredibly useful for solving problems where you have that specific mix of knowns and unknowns. And with a little more manipulation, we get another rule that should look pretty familiar, the spherical law of sines. Just like its counterpart in plane geometry, it reveals this fundamental symmetry in the triangle. It tells us that the ratio of the sine of a side to the sine of the angle opposite it is constant for the whole triangle. Okay, now let's do something that scientists and mathematicians love to do. Let's examine how these general formulae behave under a specific simplifying condition. What happens in the special case of a right-angled spherical triangle? So what happens to our formulas if we just simplify the situation a little bit? Let's take that special case where one of the angles, let's call it angle A, is a perfect right angle, exactly 90 degrees. This has a really powerful simplifying effect because, as we know, the cosine of 90 degrees is 0 and the sine of 90 degrees is 1. Let's look at the five-element formula again. You see that final term? It contains the cosine of A. So if angle A is 90 degrees, cosine of A is 0. And that entire term, it just vanishes. It's gone. And it leaves us with a much more compact, much cleaner expression. After simplifying, we get this really neat special case relation. And this is a great example of how mathematicians and physicists work. We often test general formulas under specific conditions to find simpler, more direct tools for specific problems. All right, section 6, the Astronomers' Toolkit. Let's bring this all back to where we started, looking up at the night sky. Why did we go through the trouble of building this entire mathematical system in the first place? Well, the answer is that this entire system, the law of cosines, the law of sines, all of their derivatives, this is the engine that runs observational astronomy. It allows us to perform absolutely essential calculations, like converting the coordinates of a star from where it appears on our local horizon to its fixed position on the celestial equator. Without this math, our view of the cosmos would just be a disconnected jumble of points. This whole exploration is just a powerful reminder that mathematics isn't just some abstract game. It is the language we use to describe reality. The non-Euclidean geometry of the celestial sphere, and, for that matter, the warped space-time of general relativity, forces us to ask a really profound question. What other parts of our universe are governed by rules that fundamentally defy the intuition we've built living in our flat, everyday world?
Thank you, friends. Strive for understanding and become wiser. See you soon.